so far what we looked at was static characteristics, which is basically voltage transfer characteristics, and also noise figure, which you can find out from the VTC. Now we are looking at dynamic characteristics. So dynamic, the word signifies characteristics, how it changes with respect to time. So time is the independent variable with respect to which we are looking at the variation of the output voltage. So earlier we were looking at static case where we keep the input at a particular voltage and we look at the steady state value of the output. Okay, we assume that enough time has been gone and the voltage is at a particular value, a steady state value, and then again we vary the input, we wait for some time for the output to reach the steady state, and this way we scan the input from some minimum value to some maximum value and see how the steady state value at the output changes. Now we are looking with respect to time. Okay, we are not waiting, we are looking at the transient response, the changes with respect to time. So for quickly understand or find out an estimate of the dynamic characteristics, we will use the inverter RC model. So let me draw the inverter circuit once again. We had a PMOS on the top, which is connected to VDD, and then we have an NMOS, which is one side connected to the ground, and the gate of both PMOS and NMOS are shorted, and that is where we give our input, and output is taken from the drain of both transistors which are connected together. So this is our output. So this is drain, source and gate of NMOS, and drain, source and gate of PMOS. So this is our circuit. So in order to see the dynamic characteristics, we will bring in the RC model with a switch, okay, for replacing NMOS and PMOS. So if you look at the capacitors, we discussed various types of capacitors. We said there is a gate capacitance, then there is junction capacitance and overlap capacitance. These are the three types of capacitance, and then we distributed these capacitance with respect to different terminals. So if you take an NMOS, what we earlier saw was NMOS like this. Okay, so it had various capacitances, and we said there is a capacitance between gate and, so this is our C G S. So let's assume that this is source, and this is drain, and this capacitance is CGS. And similarly, this similar capacitance between gate and drain. So this is our gate. We had also a fourth terminal. Okay, so which was also called bulk terminal, and there was capacitance with respect to that also. So this is our CSB, and similarly we have capacitance. These are junction capacitance basically, CDB. Okay. Now if you look at the signal is going to flow from source to drain, okay, or drain to source in the case of NMOS transistor. We can simplify this capacitors by taking the all the capacitors connected to the drain terminal and combine it, and then assume those capacitors are connected to the ground. Okay, so let's do that. So I'm going to redraw this circuit. This is NMOS transistor. So this is our gate, this is our source, and this is our drain. And what I'm going to do is that I'm going to distribute all the capacitors. I'm going to combine all the capacitors which are connected to the drain terminal, and I will approximate it by using one capacitor. Okay, so this is our you can say CD okay, what we can call it as we can call it as CDN also, for because we are looking at NMOS, so let's call it as CDN because it is NMOS. For PMOS we will call this capacitor as CDP. Similarly, I can take whatever capacitors connected to the source, I will call it as CSN. Okay, now what is CSN and CDN? That I have not told earlier, but now I am giving you the definition for it. CSN is basically CSB plus CGS. Okay, so these two capacitors, one is with respect to source and gate, another is with respect to source and bulk. Okay, because this terminal, bulk and gate, it will go to some power supply, right? So either the signal supply or bulk is going into it will be usually grounded for NMOS. So we can consider for AC equivalent model, we can consider all the capacitors which are connected to the point source point, we can consider as grounded like this. And similarly, all the capacitors connected to the drain side. This is a simple model. We want to simplify the model as much as possible. And then we have a switch and a resistor here. So now if I further replace the channel also with a resistance, I can now draw it as some resistance which we will call it as Rn, and then some switch, and then this is our CSN, and then this is our CDN. So this is our source terminal, this is our drain terminal, and the operation of this switch is controlled by the gate voltage. Okay, so gate is somewhere here. So this is an equivalent model, very simplified model, but it is useful to estimate some of the time constants by which the dynamic characteristics can be specified. So similarly, we can also talk about the PMOS. So in a similar manner, we can replace a PMOS with the following simplified RC model. Okay, so let me also draw that. It will be very similar. So instead of Rn, I will have Rp, and let me say this is drain. Then I have a switch which is controlled by the gate terminal voltage. So this is my gate and this is my source. I will have capacitors connected to the ground. This is called CSP and this is called CDP. Okay. So I have now the models for NMOS and PMOS, which I would like to now put into this inverter circuit. So inverter RC model. Let us draw. RC model. So this is the model that we will use to derive the or estimate the values of rise time, fall time, propagation delay, etc. So we will replace. So here is our VDD again. Now there is going to be RP, then there is a switch, and here there is a capacitor which is grounded, and this capacitor is basically, because this is source, so this is CSP, and then there is another capacitor on the other side which is CDP. So this is basically our gate of PMOS. This is the drain. Okay, so drain, source and gate. And similarly again draw the equivalent circuit of NMOS. So this is Rn. So I have a capacitor here. This is my CDN. The output is taken from here. Then I have a switch. I'll put it in a box. It is controlled by the gate. Then the other side I have one more capacitor which is CSN, and then this is ground. Okay, so I replaced the two transistors NMOS and PMOS with their corresponding RC equivalent circuit in order to get my inverter RC. So now this is both connected together, and that's where I give my input. Now if you look at that, out of these 4 capacitors which I have put, 2 of them doesn't matter at all in determining our output delay at the outputs or the transient response at the output. Now output is in general also connected to some other section. So usually output of one gate will go into the input of another gate. So if I just show you here, so this is an inverter. Now that inverter may be driving another inverter like this. So there will be a line which is connecting, whose length will also depend on where the second inverter is located. Then the input of this second inverter will have some gate capacitance due to, because we are connecting basically to the gate of the NMOS and PMOS. So the gate capacitance due to even if the inverter is very close by, and we can neglect in that case the capacitance of the wire, the transmission line we call it. So this is called the transmission line. So the capacitance of the transmission line can be neglected if these two inverters are close by, but we cannot neglect the gate capacitance at the input of the second inverter. So this is the first stage and this is the second stage. So first stage output is driving the second stage. Okay, so there is a gate capacitance which we derived earlier for PMOS and NMOS. So that is going to be the load. So I'm going to model all the 3 things, that is the capacitance due to the transmission line, the capacitance due to the gate capacitance of the following stage, all together into one capacitance which I call here as the load capacitance. So the load is usually a capacitance, because in CMOS circuits you see that gate current is 0. Okay, so mostly the load is a capacitor, so it needs to get charged in order to raise the voltage. Now this circuit, which now we got equivalent circuit. Now if you look at the top capacitor is between VDD and ground, and it's not playing any role, no role for this, right? It is between VDD and ground, and similarly this capacitance, it's between ground and ground, so this also has no role. So we can just remove this and put in only the rest we need to use. Now CDP and CDN, this is the drain capacitance for PMOS and NMOS. They are in parallel, so you can combine them. So what we will do is that we will define CDP plus CDN. They are in parallel, so we will call it as C FET. Okay? One is due to the N MOSFET and the other is due to the P MOSFET. So both are at the drain. So we will combine them and call this is the parasitic capacitance which is going to play a role in deciding the rise time, fall time, etc. And added to that, now this is in parallel with the CL also. So C out, we will call it as C FET plus CL. Okay. So now we can replace these three capacitors which are going to play some role in the dynamic characteristics into one capacitor, because all of them are in parallel, drain to ground, and output is also taken from drain to ground. So all of them are parallel, so you can add them, but we will classify them as parasitic capacitance. So C FET is basically the parasitic capacitance. This is the parasitic, and the other one is the load. Okay. So together we call it as output capacitance. So the model gets further simplified. So let us redraw this again. So we have VDD, then resistor, switch. So this is RP, and then we have resistor, switch, ground. So this is RN. Now the expression for RP and RN we have estimated under certain conditions earlier. So whatever is that average resistance we get, we will put it here. And the evaluation that we did is for a special case where we considered velocity saturation, but that approximation need not be valid for long channel MOSFET. So now I am going to put just one capacitor which is having all the parasitic and load capacitance inside it. Okay, so this is the simplified model. So whenever we look for charging, what we do is charging is run, this is the path for charging, and whenever we look for discharging, we consider this paths. Okay, so this is discharging will decide your fall time, and charging will decide your rise time. Okay, so this is just a single RC network, and you can immediately write down what is going to be the rise time and fall time. So let's evaluate rise time. Rise time. So rise time, many different definitions are there. One definition is the time it takes to rise the output from, so this is our output. the time it takes to rise. So rise time is defined as the time it takes. This is a very popular definition to rise the output from 10% to 90% of the steady state value. Now steady state value is VDD. As you know, our PMOS is a very good candidate for passing high voltage. That's why we put them in top portion of the circuit. So it can go up to VDD, it can charge up to VDD, C out can be charged up to VDD. So if this is the definition, then we need to find out the corresponding time where the output become 10% and output become 90%. So let us denote these 2 points. So let us what we can do is we will draw the waveform and then denote these 2 points. So the output, if I draw the diagram, so this is with respect to time. So here we are looking at the dynamic characteristics. So this is the charging. Now from the RC transient analysis, you are already familiar how the waveform is going to look like. It will asymptotically charge up to VDD. So VDD is somewhere here. We also saw this in the control system, if you remember. First order, this is a first order control system. You can consider it as a first order system. And then how does the response of the step response? We are looking at the step response because switch is getting on, immediately all the VDD is coming. So from then onwards the output, so initial slope will be larger, then it asymptotically goes like this. So this is the way in which it is going to get charged. So we are talking about 2 critical points. One is the 10% point and the other is the 90% point. Okay, so 10% point is here, 90% point is here. So let's call them with some name, say U and V, these times. Okay, so let's call it TU and TV. Okay, so so this is one way to define the rise time. So V minus TU, this is our T rise. So T rise is basically TV minus TU. Okay, so I just denoted it as 2 points. One is U, so that corresponds to 10% of VDD. Another point is 90% of VDD. Okay, VDD is this much, 90% is this much. So that is our V point. So TV minus TU is what we call it as the rise time. So what is the expression for this? So it is the same expression for a step response of first order system. So if you recollect, it is given by, so let me call it as V out. So this is our V out of T. So V out of T while charging. Okay, so this is charging. So what is it equal to? Finally the steady state has to become VDD. So it is going to be VDD into 1 minus e raised to minus t by time constant is given by RPC out. Okay, so if you look at t equal to infinity, what will happen? This term will goes to 0, so you will get VDD, and time t equal to 0, it is 0. So now in this expression we have to look at 2 points. One is a 10 percentage point. So at U, point U, what is the situation? We will have it as 0.10 percentage means 0.1 VDD is equal to VDD into 1 minus e raised to minus, so this is going to be TU RP C out. So you can see this will get cancelled. We'll get some simplification. So that's going to be equal to okay, so let's write it as so this is so if I take this exponential term to the left side, it will become plus, the other term to the right side, so I will get basically e raised to minus TU by RPC out. So that is going to be equal to 0.9, right? So 1 minus 0.1 is 0.9. So now if I take logarithm on both sides, I will have TU by RPC out is going to be logarithm of 0.9. Now I can take the minus to the other side, and then I can write it as ln. So I will take the minus sign to the other side, and I will write it as 1 by 0.9. Or I can say TU is equal to ln 0.9 into RPC out. In a similar way, I can do for point U. Similarly at point V. So point V is where voltage is 0.9 VDD. So only difference is that U will be replaced with V. So we can again cancel this, and then again I will take this to left side, and this is going to become 0.1. So then, like before, I take the logarithm. What will I get? TV, I will get it as ln 1 by 0.1 into RP C out. So therefore, rise time is defined as TR is equal to TV minus TU. So that is RP C out is common, I can take it outside, ln of 1 by 0.1 minus ln of 1 by 0.9. So that is RP C out ln. So this is A minus B form, so you can write it as A log of A by B. So that is A is 1 by 0.1 and B is basically 1 by 0.9. So if you multiply with the conjugate, you will have 0.9 divided by 0.1. So this comes as 2.2. 2.2 logarithm of 0.9 by 0.1. So that is basically natural logarithm of 9. So that comes as 2.2. E raised to 2.2 is 0.9. So 2.2 rp C out. So that's the estimate. It's an approximation. The actual value you have to do simulation, but analytically, quickly, if to find out, if you know rp and C out, you can quickly find out the rise time. Similarly, you can find out the fall time. So for that we need to consider the discharging. Okay, and while discharging, what is the way waveform changes? It will be an exponential decaying waveform. So then we now go to discharging. So first of all, let us draw. So this is our V out as a function of time. Initially it is at VDD, and then it is going to exponentially discharge. Okay, so this is also a transient response, probably you might have seen in network theory. Now here also you can talk about 90%, you get 2 points, and 10% you get. Okay, you can name it as A and B. So this is TA, TB, etc. And the difference between TB and TA is what we call as fall time. So this is our 10%, this is 90%. 10% VDD, and this is 0.9 VDD. So T fall time is basically TB minus TA. Now what is TA and TB? So V out expression is given as VDD initial voltage into e raised to minus T by Rn C out. Capacitance is the same, but resistance is now different. Okay, so therefore it is rise time and fall time, if it has to be equal, you should take same resistance value for PMOS and NMOS. So that is also a thing that you need to consider while designing the inverter. Designing means all the design parameter you have to fix accordingly. That's what we mean by design. So I classified the parameters as design parameters and process parameters. Process parameters is given to us by the foundry. We don't have any way, we cannot change it, but what we can modify is the design parameters. So there are few of them which you can decide accordingly. Your Rn and Rp will be fixed. Okay, so now like before, you can for 90% it's going to be like 0.9 is equal to 0. So this is for at point A. Point A, it is 0.9 is equal to e raised to minus TA by Rn C out, which means that your TA, the TA is going to be, take the log, okay, so it is going to be Rn C out into Ln by 0.9. Similarly, at B, you can write it as 0.1 is equal to e raised to minus TB Rn C out. So it is Rn C out Ln 1 by 0.1. Okay, so you can subtract now this. So we will get similar expression, only difference is Rp is replaced with the right, we will get similar expression C out. So TB is denominator 0.1, so 0.9 divided by 0.1, so that is again 2.2 Rn Cm. Okay, so we got the rise time and fall time by defining them as 10 percentage point to 90 percentage point, or while discharging 90 percentage point to 10 percentage point. Now alternatively you can, there is an alternate definition which I earlier introduced, where you can define in a slightly different way, where you show with respect to the input waveform. So this is V in of t. So V in may change to VDD in some amount of time. Okay. So there could be a delay also for input waveform, and then we look for how the output changes. So output should decrease. Now we note down the 50 percentage point here. So output is initially at high VDD. What is going to happen is that the actual waveform will look something like this. Initially it will go up above VDD. We will do that in the Monday experiment. We will do dynamic characteristics, and this is going to be the way actual expression is going to look like, and then from there it comes down. Okay. So it will be like that. And the reason why it comes down is NMOS is off until your VTN is reached. So till that time the output is going to go up, and the reason why it goes up is because there is a capacitance, gate capacitance, which is connecting between gate and the input and the output point. Input and output point is connected by the gate capacitance of the NMOS. Okay, so when the input voltage abruptly changes, it will try to take the output voltage along with it to rise up until the NMOS is off condition. Until the NMOS is off condition, it will try to take the output voltage along with it, and that is why initially it goes up, but the moment input voltage rise above VTN, that cannot be done because discharging will start and the output has to so discharging will only happen after the NMOS is turned on, which will happen only when the input is going above VTN. So until then there could be a hike in the voltage, and that will be above VDD, above the power supply voltage. So that's because of the coupling between input and output through the gate capacitance. So that you can see. Now usually when we do inverter characteristics, we will give pulse waveform. So pulse waveform, if I give at the input, then it will have, the input can also have a fall time also. Okay, so suppose this is our fall time, and then again after some time it increases. So this is the type of input we can create in SPICE program, and then so this type of waveform we can create, pulse waveforms. Okay, so then what happens? So when the input is changing from high to low, the output is already at VDD. Okay, sufficiently it is discharged and it is reaching VDD through discharging through NMOS, and then it is coming, input is coming down to 0. So then what happens, your PMOS will be turned on after some time. Okay, so PMOS will be turned on when it is input is coming below VTP, modulus of VTP, then PMOS. So till then there is a coupling, so which will basically take it to the other side, and after that it will try to, so the steady state is VDD, but there is a dip here also, and then it goes like this. Okay, so then this thing repeats. So again it goes up, and then again. Okay, so I am showing only this much. So so because of this alternate way of, I am coming into alternate way of defining the charging and discharging time, is to consider the 50 percentage point here at the input. So this is like the 50 percentage of, that is VDD by 2. So this is VDD, 50 percentage of that, and wherever the line meets, you drop a perpendicular, and then also take the 50 percentage of the output, that is, okay. So this is an alternate way of defining. This is how earlier we have, so this is also called fall time, and similarly the same 50 percentage point you take here also, and this is the 50 percentage. You see that these times are really showing up very small compared to 10 to 90 percentage. So this is T rise. Now one of the important thing that we need to estimate out of this analysis is what is the maximum frequency at which I can change the input. Okay, so there is a frequency at which this pulse waveform is operating. So if you look at here, the time period is this. Okay, for some time it is at on or high state, and sometime it is low state. Okay, the input is, this is here, it is high, and then it is low, and again it becomes high and low. So usually we give this kind of pulse waveform into this digital circuit, which stays at high and low digital logic levels. So there is a time period associated with that, and frequency is basically 1 by T. So what is the question is what is the maximum operating frequency that ensures proper operation of the circuit. That means for inverter, proper operation means if I give high state, I should get low state. Otherwise if it is still giving high output, then it is unacceptable. So I have to ensure that. So there is a limit to which I can increase the frequency. Now what is that frequency? For example, if I take so for F max, corresponding to F max, I have a T minimum, right? Maximum of frequency is minimum of the time period. So F max is basically 1 by T minimum. Now the T minimum is basically it should be at least greater than or equal to TF plus TR. Okay, that is minimum. But you see that if there was no rise and fall time associated with the input. Okay, so here I have taken a case where the rise time is there for input also. So input also takes some finite amount of time, and as a result there was some period of time the input was rising and then output was rising, and then only it was falling down. So that is not actually in the calculation for T F and TR. Okay, so that time period is not exactly taken into account. So we need to give a correction even if you take TF and TR as I have shown in the waveform characteristics, and if I operate T minimum as TF plus TR, okay, so that may not be sufficient to take into account of this increasing voltage as well as decreasing voltage while before charging. Increasing voltage before discharging and decreasing voltage before charging. So TF and TR, earlier we found it out with this 50% analysis. What we found out that time, I didn't take this slow or rise and fall time of the input. I took abrupt change and then calculated from 50% becomes from 0 to 50% in that case. So that we got it as so TF in this calculation we will get it as 0.693. That was basically logarithm of 2. So 50% means the time at which the output becomes half. So logarithm of half will come and then if you take the inverse of that, it is log 2, and log 2 is 0.693. So fall time means it is Rn C out. Okay, according to this definition. Okay, so considering TF as the time to reach 50% VDD. Okay, from that, once the input is changed, so that will be 0. If it is abruptly changed, it is 0, and then for output to reach the 50% from 0 to 50%. I mean time t equal to 0 to time t equal to 50%. So that we will get it as Rn. We have already derived that in an earlier one. Similarly, T rise also becomes 693. That I did not derive, but as you can see, it is the similar derivation. So it is only difference is Rn will be replaced with the. Okay, so if we put that those values here, so this is 0.693, then Rn plus Rb into C out. So this is going to be the T minimum, where I did not include any rise time and fall time for the input. Okay, so input signal is abruptly varying, so this I have to specify also for abrupt input signal variation. Okay, so therefore F max is basically 1 by of this. Okay, so whatever it be the value, you will get it as the maximum. Usually it will be of the order of 1 gigahertz. It will depend upon the design of capacitor, MOSFET, that is the area, W, L, all of this is going to determine your capacitance calculation as well as your resistance calculation. So okay, next class we will do a problem, and then you will get a better idea of these time estimates. And also, like in the next lab, we will do the dynamic characteristics and we will see these waveforms, and or you can study the effect of these changing the W of NMOS and PMOS, how it is going to change the value of this rise and fall time and the maximum operating frequencies. So today we will stop here.